Talk about the OSIRIS-REx mission, and I thought the previous video with its calming, soothing mood, I thought was just ready for the next video I was going to show as part of my one. So let's move this. How do I make it go?
There's been nothing like OSIRIS-REx in NASA's repertoire. I like to call it the Daredevil spacecraft.
10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Yeah, it's not quite the A34. But I think the end of that, it kind of reveals the sort of Dyson vacuum cleaner head thing in there, which is what we collected the sample in, called the touch and go sample mechanism. Kind of sums up the thing, right? It's a box of expensive rocks. You know, why do we care about a box of expensive rocks and go to all this effort and bring it back to Earth? So what I'm going to talk about today is why you went to the effort to do all this work. I'll mention what's been going on here in the UK. Although my name was on the talk at the beginning, there's a large team in the UK at many universities looking at the sample and explaining why it matters and what we're going to do here in the UK a little bit more. And what are we doing next as the sample going on? So we've got our box of expensive rocks. Why did we go to all the effort? Well, here's a picture from our late colleague, Professor Fred Taylor, from one of his books. And this is the sort of standard picture that we have of how the solar system formed if you go to a regular textbook. You got the kind of large diffuse cloud, which is cold enough and big enough so that it starts to collapse under its own gravitational pull. You know, when you get a little bit of a disturbance, starts spinning, makes a sun in the middle, boom, the Tori phase blows all the stuff away, and then leaves you with, you know, your proto-solar system. The thing is, of course, in every single one of each of these steps, there is lots of information missing. And trying to piece all that together to understand how you build planets and how we end up with oceans on the Earth and where did all the organic stuff come from is actually really quite complicated and an important part of this story that links us all the way from me standing here today all the way back to the large diffuse gas cloud, which came from the original supernova explosion that made the solar system. So asteroids are a really good way of us sampling and understanding how the solar system formed, because they're kind of free sample return, right? Material from space is always falling onto the Earth and other planets, obviously. I mean, we see meteorites on the surface of Mars, for example, from Mars rovers. And what we find is that the meteorites fall into different categories. And what they kind of represent crudely is the formation processes that happened in the solar system. So the most primitive, as we date by using isotope dating techniques, are things called carbonaceous chondrites. These are the sort of speckly rock things where you've got these tiny little things called chondrules, these spherical things. And in fact, these white blobs, the calcium aluminum inclusions they're called, they're actually the things that used to give you that 4.678 billion year age, or whatever it is, of the solar system. They're actually the things that were used with lead isotope dating to give you the age of the solar system. But then as you form protoplanets and as things start to freeze out and heavy stuff sinks to the middle and you get differentiation, all that kind of thing, we can also see evidence of this process in the different types of meteorites that are recovered on the Earth. So you've got carbonaceous chondrites, which are the most primitive material, and when you look at them in a museum or something, you can see they're almost like little bits of grit all stuck together from the protoplanetary nebula. And then they form ordinary chondrites as they start melting and being altered by different processes. And eventually you get these fantastic things called pallasites, where you've got blobs of nickel and iron from the sort of molten core of a protoplanet as it's forming, which then gets destroyed and disrupted to form, gets broken apart and then turned into meteorites. And then olivine crystals, which are here, which essentially is the heavy stuff separating out. And then finally, you get big enough that you can form fully differentiated objects. So each of these steps tells us something about how you build planets, but it also tells us how the solar system as a whole was formed. And so what we'd really like to know is, you know, how do all this stuff go together? So meteorites are great. They teach us an enormous amount. And in fact, large chunks of our understanding of the solar system and formation processes and all that kind of stuff are traced from meteorites and studying them in the lab. And, you know, because in the lab, you can take your sample and you can put really big instruments on it, but there's no way you could fly in space, or at least not at the moment. I mean, a good example actually is that big donut thing next door. That's a fantastic, giant super microscope exposure thingy. You name it, you can do it on tiny pieces of samples. You take tiny things and put them in diamond. You can do amazing experiments. You can't take the diamond synchrotron to Mars yet, no matter what Elon Musk might say. But the big problem with meteorites is that they're self-selecting, right? They've got to survive landing on Earth. The Earth's atmosphere is a great barrier for burning stuff up. That's why we don't have loads of impact craters everywhere like we do on the moon. And we don't have very much information about where they've come from. It's very rare that you can actually track the incoming meteorite to a trajectory and go and collect it quickly. And so you can then reconstruct it and know where in the solar system it came from, and then try and understand and reconstruct its dynamic history. I mean, the most recent example is the Winchcombe meteor, which fell again during the pandemic. And that was great because there's now a network of cameras which monitor the sky constantly in the UK, in particular around the world, but also there's quite a few of them in the UK. So they were able to see this thing coming in, the Winchcombe meteorite, reconstruct the trajectory, and then people ran out and collected it. You know, and we were very lucky that the family when it landed on their drive, you know, quickly put a margarine tub or something over it to protect it. And before the Natural History Museum and colleagues got there to curate it. So that was one of the rare ones. Normally we find meteorites that are all, you know, scattered. We get them from Antarctica or the desert, and we don't know how long they've been there because they're little black rocks on yellow surfaces or white surfaces, depending on which part of the world you're in. So what you really like to know is where did it come from? So, and if you want the most primitive material, you've got to go to a primitive asteroid. That's okay. We know roughly from spectroscopy by comparing meteorites to asteroid spectra what we think a primitive asteroid would be like. But you've got to choose your primitive asteroid carefully because you've got to go to one that you can reach and be sampled. So it's got to be an object that you can get within the budget available to you of a New Frontiers or ESA medium class type mission. So €1 billion or less if it's ESA, depending on how you count. And you've also got to hope that when you get there, the terrain is nice and smooth and sampleable. And that was, we'll find out a bit later, a bit of a problem when we got to Bennu. Then what we can do is you go to the asteroid, you map it out from a co-orbit to get the geologic context for where the samples come from, grab a sample somehow, which is non-trivial, and then bring it back to Earth. And so this is what we want to do. That way we know where it came from. We've got good trajectory information on the asteroid itself. We know the context the sample has come from on the surface, and then we can reconstruct the orbit it's been in and then work out its history. And then from that, you can start piecing together the story about solar system formation. So the other thing about sample return science is that it's sample return, it's science that lasts for decades. So although OSIRIS-REx returned probably a couple of 100 grams of material, we've got 70 grams of material out of the sample container already. There's probably a few more of the sample stuck in the actual sort of Dyson ring bit of it at the moment. Only a fraction of that is actually going to be analysed today by the sample analysis team. Most of it is going into storage, and it will be there for future generations to look at. And the lunar samples really give a great example of this. So this is a slide I got from Katie Joy, because when you want to talk moon, you go to Katie, and in the UK especially. And this is an example of work that's going on right now with the Apollo samples. So these are samples that have been in storage and available to the scientific community for 50 odd years. And we're still analysing them. You know, we use the Apollo samples today in our lab in Oxford to ground truth remote sensing data from current observations of the moon, things like Lunar Reconnaissance Orbiter and next generation instruments like missions like Lunar Trailblazer. You know, we're still analysing data to this day from the moon. And so these samples we've got from OSIRIS-REx and from Hayabusa and Hayabusa 2, we're going to be studying these for decades and decades to come. So when Bennu, which is the name of the asteroid, it was originally called 1999 RQ3 or something, I think, but they gave it a name in a naming competition, which went better than asteroid face or whatever. We looked at the thermal properties with, say, the Spitzer telescope, and everybody thought it's going to be smooth, it's going to be lovely. We're going to just sidle up with this thing, stick out our proboscis job with our touch and go sampling candle, touch onto it, fire the reverse vacuum cleaner because it dumped a load of gas, pure nitrogen gas, which then pushes it into the filter and catches it. Magic. And about the same time as the mission was launching, a Japanese mission called Hayabusa 2 went out to an asteroid called Ryugu. And Hayabusa 2 thought they had the same sort of situation, got to their asteroid, and then it looked, well, not like this because this is Bennu, but just as bouldery. And the OSIRIS-REx team went, well, ours isn't going to be like that, it's going to be fine. And then we got there and oh dear, it was very, very bouldery. Now, bouldery in asteroid terms is kind of interesting because these things are really loose piles of rubble. And I'll show you why we know that, because when we actually did the touch and go sampling on it. But essentially, this was not what we expected. We expected it to look roughly like this shape, which is called a Yorpoid, because it's kind of been spun up by the sun's radiation pressure, differential heating and cooling, and then that pushes things out. But essentially, we didn't expect it to be this complicated. So what we were doing was, in the UK, while we were at the asteroid, and they were planning ways of doing the sampling, was we did loads of work in the laboratory, doing spectroscopy measurements in our lab in Oxford. We're using analog materials to try and match what the material properties of the surface were. At the Open University, Ben Rositas was busy taking all the thermal data and doing thermal properties mapping. And then we're getting ready to help select the sample site, because now we know it's so bumpy and lumpy, selecting the sample site became really more challenging. And in fact, they had to redo the onboard flight software on the spacecraft in order to do guidance and navigation to actually autonomously bring the spacecraft down and then do the touch and go sampling. This is the actual touch and go sampling event in 2020. And they touch the end of the probe onto it. And then, is it going to do it? I think it is. It's a bit slow, but slowly pulling it in. You can see how the spacecraft is essentially navigating its way around these different targeting ellipses, touches onto the surface, and then, come on, hurry up. There we go. Oh, hang on, it's going all the way in. It didn't stop. It kept going, and it just blew all this material out of the way. This was a really poorly consolidated object. And then the spacecraft backed away quickly so that it didn't have a problem. So anybody who sort of sees science fiction things where they go up to an asteroid and like have people crawling over it, things like that, that's almost certainly not what would happen. It'd be an incredibly dangerous environment to be in. We actually got too much sample in a touch and go sample head. So this is the image after sampling, and you can see the stuff escaping out into space. This made the principal investigator, Dante Loretta, whose name I should have mentioned at the start of the talk, at University of Arizona, go, right, stick it in the sample capsule now. They originally were planning on sticking it on an arm and spinning it around to measure the mass. They said, no, get it in the capsule, preserve the sample. 24th of September, it came back to Earth, very conveniently landed point down, which was brilliant. The parachute didn't work quite right, and that's quite an interesting story I don't have time to talk about, but it did work okay in the end. And it conveniently landed near a road. So it was nice to just load it onto the van and get it to the local clean room. So what's happening right now is that it's in the sample canister has been opened. They found lots of samples. All this black dirt stuff is actually Bennu. It's actually material that's in around the capsule. We think there's about 250 grams or so. That's not confirmed, but lots of things going on. It's in a curation facility and a glove box at Johnson Space Center, but they've been very carefully removing material. In fact, this is essentially a picture of it before they started removing some of the larger rocks. So you can see this is actually underneath this ring is where most of the finer powder sample is. This here is where some of the larger bits are, and there are actually some big bits of sample which were stuck in the sort of plastic flaps, the Viton flaps that were used as part of the assembly to do this one-way valve. So what we're doing in the lab is we've got different hypotheses that we want to test, and this whole large international consortium is now gearing up to look at the sample. And we're working around areas to do with, for example, how does the old sample compare with observations from the spacecraft at Bennu? How do we can ground truth the data with the real sample now? And also that can then feed into how does the sample change since the collection? That's what we're doing kind of in Oxford, as well as these are the subsidiary questions for us because we're doing remote sensing tie-up laboratory spectroscopy, but other groups in the UK are very much involved in all aspects of these questions. This is a quick look at the sample. I'm not allowed to talk about very much until Professor Loretta in Arizona talks at AGU next week. But here are some electron microscope images of some really nice little iron sulfide crystals, which are actually from inside the sample. You know, we expected to see these, but it's quite nice to see the sort of crystalline shapes embedded there from the early solar system, plus all sorts of interesting evidence of aqueous alteration and other processes that happened on the parent body before it became Bennu, and then we collected a sample of it. The first samples are now here in the UK. So the very early samples went to the Open University, and they did some quick analysis on some of those dust grains that you saw, that black material, and they were doing isotope ratio measurements to show that those dust grains really were from Bennu. They were not from the Earth as contamination. They really are from Bennu, because you can tell by looking at oxygen isotope ratios. The Natural History Museum, with Sarah Russell and Ashley King, they're doing powdered X-ray diffraction to look at analyze the bulk composition and hydration. Some of this sample will be coming to Diamond, so there will be some stuff going on next door. That's got completely scrambled for reasons I don't fully understand, but basically there's a lot of work going on at the Open University right now, where they're doing these very high precision isotope measurements and elemental abundance measurements, essentially to provide detailed understanding of the composition, and the composition then tells you about the processing history of the sample. At Manchester, they're using their big noble gas and xenon, chlorine, and halide halogen, samples analysis systems with their mass spectrometers to again look at how those trace gases such as xenon and also chlorine, bromine, etc., have been tracing how the actual material has been altered on the asteroid and previously on the bigger asteroid that it came from. And there's an enormous amount of work that's going to go on with the sample at Manchester. And then finally, down the road in physics in Oxford, we're waiting for bulk regolith sample. They're working with tiny, tiny grains, like individual grains, micrograms or milligrams of material. We need like chunks of it, frankly, to do our experiments, because we're comparing to what was measured by the spacecraft. And so we're going to put them in our thermal emission spectroscopy setup and then tweak the thermal environment so it matches spectrally what we saw at Bennu, and then we can apply that to other data sets we got at Bennu to reanalyze the orbital reconnaissance data. So there's a lot going on. I'm just plugging there in that list of things there, that all the different missions that we're doing in Oxford, because I figured I may as well use this as a cheap advert. But you know, this is the laboratory setup. If there's anyone from UKRI audit in the audience, because I know this is UKRI, that is not furniture. Okay, very important. That's actually the sample cabinet, nitrogen purge cabinet. We're going to keep sampling when it gets there. I say that because I get problems with plastic boxes for carrying flight instruments around. They think it's stationary. Anyway, right, on that, I'll finish. Thank you.
Thank you very much, Neil. I think we've got time for one quick question from in the room or online. Anyone there?
I have a question.
Oh, yep.
So did I understand?
Hello?
Hello, yeah. Did I understand correctly that when it tried to land, it went through it?
Yeah.
Okay,
Yeah.
that's absolutely wild. All right.
Yes. These objects are at the limit of their dynamic stability usually, because they're being spun up by the sun heating them up, and then they cool. They get sort of heated up evenly on one side, and then they cool unevenly, and that spins them up. And that means that they get forced into this kind of spinning top shape, because everything goes to the equator. And in fact, you can even spin off like satellite mini moons get produced that way by them. And they are almost certainly at the limit of dynamic stability and held together more by van der Waals forces than actually the gravitational mutual attraction. So it's crazy. Yeah.
Great. Thank you very much, Neil. Okay.